Alright, this is additional example set number 6. Number 1. Stacy sold 80% of the tie-dye t-shirts she took to the Green Valley Music Festival. If she sold 42 shirts, how many shirts did she take? Alright, so let's number this. Number 1. So one way, if I'm not sure what to do, is to define a variable. Let's say x represents what they're asking, and they're asking for how many shirts she took. So let x represent the number of shirts that she took to the festival. Then they say that she sold 80% of the shirts. So 0.8x. And they also say that she sold 42. So 80% of the number she brought should be 42. And then it's simply a matter of solving for x to get 42 divided by 0.8. There was nothing to remember. It came out of my equation. So x is equal to 52.5. So then you can say, oh well, if I round that to 52, then 80% of that is 41.6. If I round that to 53, then I get 42.4, so it's hard to say exactly. I'll round it up. So she took 53 shirts. Our next example is number 2. DeMarco Jones makes $13.95 per hour, but is getting a 5.5% increase. What is his new wage per hour to the nearest cent? So this is a straightforward question. I simply need to calculate for number 2 his new wage is 13.95 times, it's an increase of 5.5%, so 1.055. What do I get? 13.95 times 1.055. So I get 14.71725. So his new wage is $14.72, rounded to the nearest cent. For number 3, a laptop computer that was originally priced at $2,400 now sells for $2,700. What is the percentage increase? So, for that, let's say number 3, what is the difference? Or the price increase in dollars? Well, clearly it is $300. So then the percentage increase is the difference as a percentage of the original amount. So I get 300 as a percentage of the original amount times 100. So I get 300 divided by 2,400 times 100, 12.5%. For number 4, First State Bank loaned Doug Morgan $2,000 for 4 years compounded annually at 8%. How much interest was Doug required to pay on the loan? So I need to know over the 4-year time what amount did he owe at the end. Subtracting 2,000 from that is the total interest that he had to pay. So let's see number 4. So in this case I have a straightforward compound interest situation. So I have my original amount is 8,000. My annual interest rate is 8%, so 0.08. My compounding period is a year, so I don't need to adjust that. And I'm doing this for 4-year periods. So the accumulated amount is 8,000 times 1 plus 0.08 to the 4. That means 8,000 times 1.08 to the power of 4, 10883.91168. So at the end of the 4 years, he owed 10,883.91, let's say. The total interest then is simply that answer, 10,883.91 minus my original 8,000, so 2,883.91. For number 5, how long would it take to triple an investment at various the same interest rate of 4.5? The first one is per year simple interest. Okay, let's see. Number 5. So let's say P represents my original amount. So let's see, what would I need to have? What am I looking for? I'm looking for the length of time, so the number of periods. So in A, let's say N represents the number of years to triple my investment of P. Then I need to come up with an equation. So my simple interest formula says, well, R is 0.045, that's my interest rate. How does the simple interest formula work? I take my investment, I add the interest, and I do that for a certain number of periods, in this case years, and then I want at the end 3 times the original amount. So you can see I can divide throughout by P, and let's put in the numbers for R. So I get 0.045n equals 3, 0.045n equals 3 minus 1, so 2, n equals 2 divided by 0.045, n equals 2 divided by 0.045. 44 years, 44.44 years. So I'll triple after 44.44 years. Because it's simple interest, it's not really going to grow very quickly at all. For number 5, B and C, admittedly, I'm only putting these in to make a point, and they are not typical test questions. How long would it take to triple an investment at 4.5% per year compounded annually. The problem is very similar, except that now I have compound interest. So I'm still saying P is my original amount, and N represents the number of years it would take to triple my original investment. Then, now I have compound interest, so I take P plus my annual interest rate, P times 1 plus my interest rate to the power of N, that has to equal 3 times P. And R is, of course, my annual interest rate of 0.045. So you see the P's cancel again, and I have 1 plus 0.045 to the power of N equals 3, or 1.045 to the N equals 3. So here I have 3 options, to be honest. One is I have to use slightly fancier math, which we didn't cover in the course, so I won't do that. 2 is I can use a computer to search for the correct value of N. Since I don't have a computer, we didn't do that in the course, I'm not going to do that either. So our only method is a little archaic, but I have to just try different values of N until I find it. So let's try N equal to 24. Then 1.045 to the N equals to the 24 2.876, which is close. Try N equal to 25. 1.045 to the N equals 1.045 to the power of 25, just over 3. So my conclusion is, based on this, that it would take just under 25 years to triple my investment. Yes, there are easier ways to do this than searching. I knew beforehand to go and look between 24 and 25. You would have to just search. I can use fancier math, or I can use a computer. So it's outside of the scope of this course, but I include this just to show that technically I can look for other unknowns in my basic formulas. If I look at the C version, let's do it over here. Now N is going to represent the number of months, because I am compounding 4.5% monthly, so the number of months to triple. And R is 0.045, but now I have to look at the monthly interest rate, so I divide it by 12. So my basic formula is now the general one, and I want to triple my amount. Again, the original amount doesn't matter. I have 1 plus 0.045 over 12 to the N. N represents the number of periods, the number of months, equals 3. And I can try many different values. Let's try 292. Then 1 plus I to the N equals 1 plus 0.045 divided by 12. All of that to the power of 292, 2.983. It's close. Let's try it. N equal to 293. Then 1 plus 0.045 over 12 to the power of 293 2.994. Let's try the next one, 294. 1 plus I to the n is then 1 plus 0.045 divided by 12 to the power of 294. That is over 3. So it would take just under 294 months to triple my amount. 294 months, let's divide that by 12 and see that is 24.5 years. So I'm including these to show that we can do more interesting things if we just knew a little more math or we're a little bit more skilled with the computer. So I put these in to inspire you to learn more than what we're doing in this course, to be able to answer more interesting and slightly more complicated questions. Number 6, John has $1,000 to invest. He puts this into a savings account that gets 4% annual interest compounded monthly. After 5 years, he withdraws the total amount and then invests it in a different savings account for 3 years that gets 6% annual interest compounded quarterly. How much money does he have at the end of the 8 years? So if I just work my way through this systematically, there's really nothing to it. Number 6. So let's call this phase 1. Now P is my original amount, and my interest rate that I get is 4%, but it's compounded monthly, so I adjust it. The number of months, I do that for 5 years. 12 times 5 is 60. So my accumulated amount, let's call it A1, is then 1,000 times 1 plus 0.04 over 12 to the 60. Let's see what that is. 1,000 times 1 plus 0.04 over 12 to the 60. 12209965994. So because he withdraws it, what's going to happen? Let's round it up, for example. So he gets, let's say, 1220, and well, if it's rounded up, it'll round to 21. Perhaps the bank throws away that fraction of a cent. We can argue both. Let's round it up. Let's round it to the nearest cent. Now in phase 2, I start with, let's call this P1 and R1, I1, and N1 for phase 1. My second starting amount is now this 1221. My interest rate for the second phase is 6%. Yes, I have to adjust that to a quarterly interest rate, and the number of months, not months, quarter of a year, number 4 times 3, I have 3 years, so that is a 12. So now the amount that I get at the end of phase 2 is 1,221, 1 plus 0.06 over 4 to the power of 12, and I get 1221 times 1 plus 0.06 divided by 4 to the power of 12. 1459 849787. So he gets at the end 1,459.85 cents if we round to the nearest cent. For number 7, suppose you have an investment that earned compound interest every year. For the last 6 years, the annual interest rates in percentage were as follows. I have 5, then 15, 5, 15, and so on, fluctuating. It's advertised that you'll get an average interest rate of 10%, clearly because the average is 10%. What is the actual interest rate that you receive? So let's try and find the equivalent interest rate. Let's say R represents the equivalent interest rate. What do I mean by equivalent? The interest rate that gets me the same end amount if I replace it and have the consistent interest rate R every time. Well, I have 6 years there, so then using an original amount of P, I have P times 1 plus R to the 6. That is how much money I would have after 6 years if I have a constant interest rate of R. But using the table, I would have my starting amount, then I increase that by 5%, then I increase that by 15%, then 5%, then 15%, then 5%, then 15%. So I can divide both sides by P. 1 plus R to the 6 equals, let's just see what that is, 1.05 times 1.15 times 1.05 times 1.15 times 1.05 times 1.15. 1.760602922. So now this is a little outside of the scope of the types of equations that we've been looking at, but if I want to get rid of this 6, I would have to take the 6th root, or take that number to the power of 1 over 6, and then I have to subtract 1 to get R equal to, I could just use that number, to the power of 1 over 6 minus 1, I get 0.09886. That means that I get an interest rate of 9.89%, not the 10 that was advertised. This is a different kind of average because it's a different type of interest rate, different type of investing. So the ability to be aware of these things and think carefully and be able to calculate what's actually happening is absolutely crucial to not get tricked into going for a certain investment when the advertised interest rate is not actually what you're getting. For number 8, Pat wants to pay an ordinary annuity quarterly at 8% annual interest, compounded quarterly, to establish supplemental income for retirement. How much will Pat have to pay to have $100,000 at the end of 7 years? So now I have an ordinary annuity in number 8. I want, hopefully just one thing, and hopefully in my formula I have everything else. So I have my target end value of 100,000. I have my payment as the thing that I'm looking for. My interest rate is 8%, 0.8. I'm doing this quarterly, so I have to adjust that to a quarterly interest rate. How many periods do I have? 7 times 4 is 28. So I know my basic formula as this. I can adjust that to solve for R, just like we have done in class. And so I can put it in. I is 0.08 over 4 times my 100,000. Put that over 1 plus I to the 28 minus 1. Let's see what we get. You can do this in pieces, you can do it in one go, it doesn't matter as long as you're able to do it. 0.08 divided by 4 times 100,000 divided by, I will put that in brackets, and I'll have another bracket, see, 1, 2 brackets, 1 plus 0.08 divided by 4, close the one bracket to the power of 28, minus 1, close the other bracket, enter, 2698.967164. So I don't know if it's a him or a her. So the payment should be $2,698.97 to reach my goal of 100,000. For number 9, you have carefully examined your budget and determined that you can manage to set aside $250 per month. So you set up an ordinary annuity of $250 monthly at 7% annual interest compounded monthly. A. If you stick to your plan, what would the value of the annuity be after 10 years and how much interest did you get in total? Okay, that's the straightforward question. Now I want to know the future value, the accumulated amount. I have a payment of $250. My interest rate annually is 7%. I am paying monthly, so I have to adjust that by dividing it by 12, and I'm counting the number of months. I'm doing it for 10 years, so 120 months. So I have my straightforward formula, which is R1 plus I to the n minus 1 over I. So let's put that in. So 250 times 1 plus 0.07 over 12 to the 120 minus 1 over 0.07 over 12. Let's put this in brackets too. Let's see what we get. 250 times bracket 1 plus 0.07 divided by 12, close bracket to the 120, minus 1, close bracket, divided by 0.07 in brackets, divided by 12, close bracket, enter, 43271.20182. So how much would you have? So I would have $43,271.20. What amount did I put in? So let's say a total of my payments is 120 payments of 250 each. Let's see, what is that? 120 times 250, that is 30,000. So I put in 30,000. So the interest is my end amount minus what I put in, so that's simply 13,271.20. Now let's look at the B question. After 5 years, you now review your budget and determine that you can only deposit payments of $200 per month. If you follow this plan for another 5 years, what is the value of the annuity after 10? And what is the total interest now? So I'm doing the same thing for 10 years. Sorry, I'm doing the whole thing for 10 years. But 5 years in, I stop, look at my amount, and say I'm changing my payment to $200 per month. What happens now? Let's say this is 9B. So I have to look at the first 5 years. I want to find the end amount. My payment is $250. Same as before, I get 7%. Everything is still monthly. And I'm doing this for now only 60 months. So what I get is $250, same as before. I'm just doing it for half the time. 1 plus 0.07 over 12 to the 60, out of that minus 1 over 0.07 over 12. Let's see what we get. It's not the previous amount divided by 2. Let's see. 250 times bracket bracket 1 plus 0.07 divided by 12, close the bracket, to the 60, minus 1, close the bracket, divided by 0.07 divided by 12, like so. I get 17,898.2254. Alright, so now I stop and I say I need to adjust my payment. So it's crucial here that I understand how we derived the formula. So let's do it on the right hand side here. At the end of month 60, I have my 17,898 and 2254 at the end of month 60. That's how much money I have. Now, going forward, I look at month 61 and I say the previous amount sits there. Let's call this something else. Let's call this A5. Actually, no, let's call it A60 because I'm counting the months. So let's call it 60. And instead of this messy number, numbers are so messy, let's instead just call this A60 is what I have. Now at the end of my 61st month, that amount sat for a month, excuse me, so that gets increased by my interest rate I, and I now add my 200. I'm not deriving the whole formula, I'm just getting an idea of what the calculations are that are involved here. At the end of month 62, I've lost the ability to write numbers now. at the end of month 62, what happened? Let's call this A61. A61 sat there for a month, got increased, and I add another 200. Let's call that A62. But before we do that, let's refine this and show the calculation. Instead of A61, I'll put in this to get A60 plus I squared plus 200 plus I plus another 200. Let's do one more. For the next month, my previous amount that I'll name like this sits there, gets increased, and I add another 200. So, what happens now? This gets put in place of A62 to get A60 times 1 plus I cubed plus 200 times 1 plus I squared, 200, 1 plus I, plus my 200. So we see that this is now separate from this list. So I'm essentially, even though I add the 200 now periodically, I'm still continuing my annuity. I can essentially view the calculation in two parts. One part is a brand new annuity where the 200 starts from scratch, builds up interest, and so on. The other bit is the carryover amount that sits there and gets interest for the remainder, for the next 5 years. So, what I can do is, for the second 5 years, I don't want to just see this intuitively, because then as soon as things change, I have no confidence that I'm correct. But understanding how these formulas are derived gives me confidence in my calculation. That now my calculation comes in two parts. I have the previous A60 amount that gets interest of I for another 60 months. Added to that is the second part to my annuity, where the $200 payments now get added up and get interest as well. So that will be my annuity formula using a 200 payment, 1 plus I to the power of 60, because the length of time is 60 again, bracket over I. So I'll use this number for A60 and put it in there, and let's see what we get. If I look at this and compare it to the previous part A's, 43,271, I expect to have less because my payments are reduced. So let's see. So that tells me if I get a number more than 43,000, I probably did something wrong. So let's see. If you want, we can do this in two pieces. Let's do the first one. So I have 17,898.2254 times bracket 1 plus 0.07 over 12 bracket to the 60. That is 25,372,97642. The second part is an annuity, 200 times bracket 1 plus 0.07 over 12 divided, not divided by, bracket to the power of 60 minus 1 bracket divided by 0.07 over 12 bracket equals 14,318,58032. And if I add that to my 25,372 0.97642, I get 39,691,55674. So in the end, what's this? In the end, I have 39,691, and let's say 56 cents. Let's suppose the bank is nice and rounds up. So at first glance this might seem confusing and overwhelming, but if I understand how these things work, and I understand the underlying reasoning for why the formulas are what they are, I can easily examine this in pieces, see my calculation in more detail, and then reconstruct the formulas appropriately. For number 10, Stephen Black has just purchased a home for $455,000. Northridge Mortgage Company has approved his loan application for a 25-year fixed-rate loan at 5%. Stephen has agreed to pay 25% of the purchase price as a down payment. Again, I have multiple questions here. Let's do them one at a time. Find the down payment, the amount of the mortgage, and the monthly payment. So one thing at a time. 10A. So the down payment is 25% of 455,000. 0.25 times 455,000. So that's 113,750. So my mortgage is 455,000 minus the down payment, 341,250. Now what is my monthly payment? Well, I have my loan calculation. P is my mortgage amount, my loan amount. My payments I want to find. My interest rate is 5%, but it's monthly, so I adjust it. I have a 25-year mortgage, so 25 times 12, 300. And I have nothing left at the end. So the amount left is 0. So put it all into my mortgage, my loan calculation, which is the amount left is the loan amount 1 plus I to the n minus what looks like the annuity formula, which makes it easier to remember, and that's my formula right there. So now put it in, I get 0. Well, before I put it in, I want to solve for r with a 0 here. So perhaps it's better to put the 0 in right away and now solve for r. Same as we do in class, I should get r equal to IP 1 plus I to the n over 1 plus I to the n minus 1. Let's plug that in, and we have 0.05 over 12 times 341,250 times 1 plus 0.05 over 12 to the 300 over 1 plus 0.05 over 12 to the 300 minus 1. What is the r that I get? Let's move this over here. Okay. 0.05 divided by 12 times 341,250 times bracket 1 plus 0.05 divided by 12 close bracket to the 300, divided by bracket, bracket, 1 plus 0.05 divided by 12, close bracket to the 300, minus 1, close bracket, and I get 1837.074207. So if I want to pay off the loan, my monthly payments should be 1837, I guess, if I want to pay it off, I can't round it down or I'll have a little bit left at the end, so let's round it up. In part B, what percentage of his first payment goes to interest? What percentage of his first payment goes to interest? So let's number this 10B. So for that, I need to look at how the formula is derived. So I'll say here at the end of, I have a month, so let's say month number 1. What is the loan amount? Well, at the end of month number 1, my loan amount sat for that month, so I get interest on that month and I pay it off with my first payment. So my loan amount got increased by I%, so to speak, and I paid it off, trying to counter that with my payment. So let's see, what is the interest after first month? That is simply P times I, which is, what is P again? 341,250 times I, which is 0.05 over 12. Let's see what I get. 341,250 times 0.05 divided by 12. Let's hope it's less than the payment. 1421,875. My payment, I determined, is 1800. Let's write it over here. 1837.08. So the difference is, just for the sake of interest, 1837.08 minus 1421.875, 415.205. That is what the loan gets decreased by. My percentage interest as a percentage of my payment, interest percentage of payment is, well, that's my payment, that's my interest, 1421,875 over 183708 times 100 equals 1421.875 divided by 1837.08 times 100, 77.4%. So 77%, almost 77.5% of my first interest goes poof, interest. And I'm only paying down my loan by this much. In part C, find the total interest Stephen will pay if he pays the loan on schedule. So let's recap. This is a big question, so I'm breaking it up into pieces. Let's recap. My payment is $18.37.08. My loan amount is $341,250. So I'm doing this for 25 years. 25 years. That implies 300 months. So my total of all my payments is 300 times 1837.08, 551,124. My loan was only for 341-ish. I paid around 550. So my total interest is the difference, 341.2, not point. 341,250, 209,874. That is what I paid in interest. More than half my original loan. In part D, if Stephen made the same loan for 20 years, how much interest would he save? So now let's see what is different in 10D. My loan amount, $341,250. I'm looking for my payment. I have a new payment because now my loan is over 20 years only. My interest rate is 5%, but it's monthly, so again I adjust it, and now I'm only looking at 20 years times 12 is 240. So using the same formula as I've done previously, to find the payment that pays off the loan, let's put that in, 0.05 over 12 times 341,250, 1 plus 0.05 over 12 to the 240 now only, 1 plus 0.05 over 12 to the 240 minus 1. Let's see what I get. 0.05 divided by 12 times 341,250 times bracket 1 plus 0.05 over 12 bracket to the 240 divided by bracket 1 plus 0.05 divided by 12 bracket to the 240 minus 1 bracket is 2252.098962. So my payment now is 2,252, and round that up, so I guess 10 cents compared to the 1,800 before. The total of my payments would now be 2,252 and 10 cents times 240 months. So 540,504. So my total interest is then the difference between that and the original loan amount, 199,254, which means I would save, compared to the previous interest of 209,874, I would save, oh, not that much actually, $10,620. And E I can easily answer because I had to do that in D. How much would Stephen's monthly payment increase for a 20-year mortgage over a 25-year mortgage? Well, the monthly payment now is 2252.1, and the previous one was 1837. So, oops, sorry. So the increase in my payment is 2252.1 minus 1837.08. What is that? 2252.1 minus 1837.08. 415.02. So if I make larger payments, getting the loan off sooner, I save in interest. So in number 11, Susan Blair and her sister Sandra both purchase homes. They adjust their down payments so that each has a 25-year mortgage of $300,000. Susan gets a fixed annual interest rate of 3% compounded monthly, but Sandra decided on a variable interest rate. Sandra gets 3% for the first 5 years, then 3.5% for the next 5 years, then 2.5% for the next 5 years. A, what is Susan's monthly payment? So Susan gets a fixed annual interest rate of 3%. So that is the straightforward version of the question. Let's do 11A. So there, my loan amount is $300,000. My payment is what I'm looking for. What else do I have? I have my interest rate is now fixed at 3%. My compounding period is a month, so I have to adjust that by dividing it by 12. And then I count the number of months. 12 times 25, 300. So to pay off the loan in that time, S is 0. The amount left on the loan at this time is 0. So I can look at my basic loan equation, which is as follows. This guy is 0. Then I have to solve for R to get R equals IP1 plus I to the n over brackety guy like that. Put in the numbers. I is 0.03 over 12. P is 300,000. 1 plus I to the 300. All of that over 1 plus I to the power of 300 minus 1. Let's see what we get. So 0.03 divided by 12 times 300 times bracket 1 plus 0.03 divided by 12 bracket to the power of 300 divided by bracket 1 plus 0.03 divided by 12 bracket to the power of 300 minus 1, close the bracket, equals 1422.633942. So the payment is, to pay off the mortgage, she would have to pay $1,422.64. If we round it down to the nearest cent and not the highest, rounded up, we're not going to pay the loan off in the time. We're going to have a little bit left, so we're going to round up to 64 cents. In part B, they ask, how does Sandra's monthly payment change over the 15 years? So what is happening now is that Sandra starts out with 3%. Yes, she knows it's not fixed, but her monthly payment is calculated as if that is the percentage throughout. So we calculate for 11B, Sandra also starts with 3%. With 3%. So her monthly payment is going to have the same calculation as in part A. Her monthly payment is going to be 1422.64. But she's going to do this only for 5 years. Then everything gets recalculated. So we have to know how much is left on the loan after 5 years. So we want to know next how much is left on the loan after 5 years when she sits down and recalculates to see her payment. So now my loan amount is 300,000. My payment is 1422.64. My interest rate is 3% for this first 5-year period. I adjust it to monthly. And now for 5 years, 5 times 12 is 60. I want to see what is left on the loan after 60 months. Then that is the number that is used in the calculation for the next 5 years. So my loan formula says that S is equal to 300,000 times 1 plus I over 12 to the 60 minus my payment times 1 plus I over 12 to the 60 minus 1 over I. So let's see what we get here. Alright, so 300,000 times 1 plus 0.03 divided by 12 to the 60 minus 1422.64 times 1 plus 0.03 over 12 to the 60 minus 1. All of that divided by 0.03 divided by 12, and I get 256,516,0352. That is the amount that's left on the loan. So this is the next p-value going into the next period of 5 years. So now for the next 5 years, my P is what's left, 256,516,0352. My payment is what I'm looking for. R now changes to 3.5%. So I have to adjust that to be monthly. And how many months do I have left? So I have 20 years left, which is 240 months. I want to pay off the loan. So I use the same formula to calculate the payment as we did in A. So I take I times the loan amount times 1 plus I to the power of 240 over 1 plus I to the 240 minus 1. Let's see what we get. 0.035 divided by 12 times 256,516.0352 times 1 plus 0.035 divided by 12 to the power of 240 divided by 1 plus 0.035 divided by 12 to the 240 minus 1, close the bracket, 1487.689677. So, as suspected, I now have a higher interest rate, not by much, just a little bit, so my payment goes up a little bit. So the payment now is 1487.69. To be able to pay off the loan, I'm going to have to round up. So her initial payment is 1422. Her new payment at the 5-year mark is 1487. This is for years 6 to 10. So I have one more change, but in order to do that, I have to see how much is left on the loan at the 10-year mark. After 10 years, how much is left on the loan? So now my loan amount that I start the second phase with is 256,516.0352. My payment is 1487.69. My interest rate is 3.5%. Adjust that to a monthly, and I'm doing that for 60 months, a 5-year period from this point forward. So I want to find S, so I plug it into my basic formula. So it's P times 1 plus I to the 60 minus R times 1 plus I to the 60 minus 1 over I. Let's see what I get. 256,516.0352 times 1 plus 0.035 divided by 12 to the power of 60 minus 1487.69 times, oops, just two brackets, 1 plus 0.035 divided by 12 to the power of 60 minus 1 divided by 0.035 divided by 12, and I get 208,102.6514. That is the amount left on the loan. So this is the next p-value. Going into year 11, this is how much is left on the loan. So now to calculate the payment for the next 5 years, let's see, next 5 years. So now my payment is 208,102.6514. My loan amount. My payment is what I'm looking for. My interest rate is now 2.5%, adjusted to a monthly, and count the number of months left after 10 years. How many months do I have left? Well, I need to keep track of this. I have 2 5-year periods done, so I'm 10 years in, so I have a 25-year mortgage, so I have 15 years left, times 12 is 180, or 240 minus another 60. And to pay off the loan, my loan amount that's left after this period of time is 0. So now I calculate my R. Using the formula I times the loan amount times 1 plus I to the power of 180 over 1 plus I to the power of 180 minus 1. Let's see what I get. 0.025 divided by 12 times 208,102.6514 times 1 plus 0.025 divided by 12 to the power of 180 divided by 1 plus 0.025 divided by 12 to the power of 180 minus 1, close the brackets, and I get 1387.606025. So my payment is now lower because I have a lower interest rate, $1,387.61, and this is for years 11 to 15. So let's summarize to see what we have here. So we have Susan paying, what was the amount? Let us see here. She's paying $14.22.64. $14.22.64. Sandra is paying, her first payment is the same, $14.22.64. Then it increases to $14.87.69. Then it decreases to $13.87.61. So this is how it changes. Now in C, I'm looking to investigate which one has the better situation. Fixed interest rate or fluctuating variable interest rate. So let's see. So their first question is, some would argue that the average interest rate is the same for both sisters. And it is the same. The arithmetic average. Which sister has actually paid more after 15 years? So let's see the total paid. Total paid by Susan is simply $14.22.64 times Well, this is her monthly payment. So this is 15 years times 12 is 180. 180 months. And Sandra pays 3 times 60 months. Every 60 months it gets adjusted. So Susan paid this amount per month for 180 months. So she paid 1422.64 times 180, 256,075 and 20 cents. Sandra paid 1422 and 64 cents for 60 months, then 1487 and 69 cents for 60 months, then 1387 and 61 cents for 60 months. What does she get? 1422.64 times 60 plus 1487.69 times 60 plus 1387.61 times 60. She paid 257,876.40 cents. So this is the total that Susan paid, this is the total that Sandra paid. And you can argue they're only off by 1,800 or so. So that means that Sandra paid slightly more in total. Susan had the guarantee that her interest rate is not going to change. Sandra's interest rate did change. So even though the average is seemingly the same, she does pay a little more at the 15-year mark. And she'll pay more the more it fluctuates, if it goes up especially. So then the final question is, which sister has more still to pay off? So for that, I would have to go and look at Susan first. So let's bring Susan's calculations up again. Susan, we calculated the payment. So now let's calculate with this payment how much is left on the loan after 15 years. So let's do that on this page. Loan amount after 15 years for Susan. So now for Susan, the original loan amount is $300,000. The payment is $1422.64. The interest rate is fixed at 3%. The monthly interest rate is adjusted, and I'm looking at 15 years, which is 180 months. And I'm trying to find S. So what we're going to use is our basic loan formula, where I want to calculate how much is left on the loan after 15 years for Susan that has a fixed interest rate. So my loan amount, 300,000 times 1 plus I to the power of 180 minus my payment times 1 plus I to the 180 minus 1 over I. Let's see what I get for what's left on her loan. 300 100,000 times 1 plus 0.03 divided by 12 to the power of 180 minus 1422.64 times 1 plus 0.03 divided by 12, close the bracket, to the 180 minus 1, close the bracket, divided by 0.03 divided by 12. I get 147,329.0899. That is how much is left on her loan halfway through. No, not halfway through. 15 years in. She's over halfway. She's over halfway. Now, let's look at how much is left on the loan for Sandra. Well, if I recall what happened with Sandra. Let's recall here. With Sandra, when I looked at 11b, she made a payment, the same payment as Susan, for the first 5 years, and she had $256,000 left on the loan. Then for the next period of 5 years, the next phase, she paid $1,487, and she had, at the end of 10 years, she had $208,000 left on the loan. Then for the next 5-year period, we calculated her payment to be $1,387.61. So the only thing left to find is to know that at the end of that phase, how much is left on the loan. So that's 60-month period. So let's do that. So now, loan amount left for Sandra at the 15-year mark. So all I need to do is I need to look at year 11 to 15. My loan amount starting there was, let me get this right, 208,102.6514. The payment was 1387.61. The interest rate that she got for that phase was 2.5%, adjusted to get the monthly. My number of months will be 60, and I'm looking for the loan that's left. So it's a straightforward loan formula. So I have my p-value times 1 plus I to the power of 60 minus, yes, R, but I can put in the specific number here. Sorry about that. 1387.61 times 1 plus I to the 60 minus 1 over I. Let's see what I get. 208,102.6514 times 1 plus 0.025 divided by 12 to the power of 60 minus 1387.61 times 1 plus 0.025 divided by 12 to the 60 minus 1 divided by 0.025 divided by 12 is 147,194.768. So when I compare this, let's put them sort of side by side here. Let's do it like this. The loan amount left for Susan is $147,300. The loan amount left for Sandra is a little bit less. A little bit less. So when we look at the numbers here at the top, the total paid, Susan paid $256,000, Sandra paid $257,800 more or less. So Sandra paid about $1,800 more in total, and she has only not even 200 left, 200 less left on her loan. So what does that tell me? It means that by a small margin, Sandra is a little worse off. Now the margin is so small because my interest rate only fluctuated twice and not by a lot. So the margin is not that big. So you can argue that it's pretty much the same. If you want to split hairs, then Susan is in a slightly better situation. I would say that she definitely is, because her interest rate is not going to change. Who knows what's going to happen to Sandra's interest rate in the next 2 5-year phases before she's done with her mortgage. Even though the average, the arithmetic average, is the same as the fixed interest rate, the effect, because of interest and compounding and all those things, is that she pays a little bit more in total. If you're looking at large numbers, so 1,000 and 2,000 as a percentage of 250,000 is not anything people will worry about, and that's why they can get away with saying, oh, take the average of these interest rates for a variable interest rate, and if there are 3, the effect is the same. Technically no, but the difference is so small that it doesn't really matter to people in general.